Some of you have heard me tell this story before, but this is my AP exam, 1998, and this was the actual BC question that we had, and I remember this because we had never done Euler's method. So here's how I figured it out, having never done that. Just a minor amount of physics. We have a differential equation given by this, and that's one that we're going to be able to split. I don't necessarily need to draw a slope field for that, but let's go ahead and do it because the question asked for that. I didn't know what a slope field really was. I just figured that if we plugged in specific points, then I could get a slope and just draw like a little line segment on that. So that's what I did. At every single point I plugged in and found a slope. So let's try this. And I'm going to hit pause while we do this. You don't have to listen to the whole thing, but go ahead and draw your own slope field. Do not copy this. You need to have practice doing this on your own because you're going to have this on AP exams. So here's what I calculated for all the different ordered pairs in terms of a dy dx, plugging those points in. If I draw a slope field, 1/2, 1, and 3/2, I just know I need to make 1 be kind of the perfect diagonal, 3/2 be steeper than that, and 1/2 be not as steep as that. And then, but not quite, 0. So that's probably better. And then each of those is 0. And then these are the opposites, or the mirror images of the other ones. So 3/2, 1, and 1/2. Right, darken those. And that's about what you see. And I'll let you just kind of sketch those in as best you can, realizing it is just a sketch. So this is partially what you should see, or probably what you should see. Then it says, let f of x be the particular point, or particular solution with initial condition f of 0 is equal to 3. Now, if I know f of 0 is equal to 3, then I know my starting point, or a starting point on this graph is going to be right here at 0, 3. And it says, using Euler's method, which I had no idea what that was, start at x equals 0 with a step size of 0.1 to approximate f of 0.2. Well, it says a step size of 0.1. So what I thought is, we're starting here, and if I were to go over 0.1, which means that now instead of an x of 0, I have an x of 0.1. So I've got this point 0, 3. And if I move 0.1 to the right, about what would that be in terms of a new ordered pair? Well, since the slope here is 0, really my y should stay the same. Because if I zoom in on this part of the slope field, and let me erase this here, I have a slope of 0. And I'm starting with a point here, and then I want to move 0.1 to the right. But that slope of 0 is telling me that my y is not going to change. And so that told me that if my x is 0.1, my y will also be 3. And then what I need to do is say, okay, we have a new point. And what I want to do with this new point is I want to calculate the slope here. So I'm going to calculate the slope at this new point. So the slope is 0.1 times 3. So my equation up here, my differential equation, is dy dx is equal to xy over 2. Well, if I plug in 0.13, I get 0.3 over 2. 0.3 over the 2 is the same as 3/20. So now I have a slope of 3/20. Okay. So we're going to do the same thing now. I'm going to walk over one more step, 0.2. And I'm going to add that and get, that's the next one with a step size of 0.1. And then I have 3. Now I need to go from 3, and now I need to go up 3 and over 20, but only to where x is, 0.1 over. So the way I can do that is I can say, well, if this is the y value here, I want to do a better y value. I want to change the y value. Another way to say this is I'm basically like right here at this point. And now I want to go up 3 over 20, but just over a little bit. So I've got to figure out what that change in y is going to be. Well, if I take 3, which is where I am, and I add what 3/20, which is the slope, times the change in x is going to be, which is the difference of where I was versus where I was before, that should get me it. Think of this as being kind of like a y equals mx plus b. This is like a b plus mx right here, where the x is actually a delta x, the m is a slope, and then the b is like a starting y value. Now, what I get is basically 3 plus, this is 3/20 times 1/10, or that gets me to 0.2 comma 3 plus, this is 3/200, or 0.2, 3 plus 3/200 is 603/200. So my approximation, if I kind of finish up, for f of 0.2 is 603/200. And that is an approximation because it's not actually what's going to happen if I was actually on the graph, but it's close. Now, that looks complicated. I promise you it's not that bad. Let's try this other one. Okay, now it says find the particular solution to the differential equation with the initial condition of f0 equals 3. Particular solution means we're going back to differential equations. So I've got dy dx is equal to xy over 2. I'm going to split this up, so I've got dy over y equals 1/2 x dx. If I take the integral of both sides, I get ln of y is equal to 1/2 times x squared over 2, and then plus a c value. And if I use my initial condition, I get the ln of 3 is equal to, that'd be c. So then I can go back to this and say ln of y is equal to x squared over 4 plus c, or y is equal to, this would be e to the x squared over 4 plus c. And if I change this from, oh, I don't need c anymore. Sorry, we have that as ln of 3 plus ln of 3. So this is y is equal to 3 e to the x squared over 4. And if I say, well, what is y of 0.2, or f of 0.2, I should say. Let's kind of pause and I'll calculate this in the calculator. And I get 3.03015, which has an exact value of actually 3 e to the 0.2 squared is 0.04 over 4. So that's just kind of what I plugged in. But that was the approximation, and 603/200 simplifies to, a second, that was 3.015. So you can see how close they kind of are. And I was thrilled when I got them to be that close, because that meant I probably did it right. And in fact, I did. So yay me. This is called Euler's method. And if you read this, it's a first-order numerical procedure. First order meaning kind of linear. But it also really, in terms of first order, it's not linear. That's incorrect. That's first degree. First order means first derivative. It's first derivative only. So think dy dx. So no y double prime or anything like that. First order procedure for solving ordinary differential equations with a given initial value. It is an approximation, so there's an error. And the error is proportional. You don't have to memorize this. But it's proportional actually to the square of the step size. Step size is what our kind of, well, in the previous one it was 0.1, but it's however much we're walking by. And the global error, meaning the error of the whole thing, is really just proportional to the step size. So the smaller the step size, the better approximation you get. I kind of wrote this next part. Euler's method for differential equations of the form dy dx is equal to f of xy. What that means is that something like this, that's that form where the right side is just an equation and the left side's dy dx. That's just an example, though. Uses a starting point and a step size to walk along the slope field and generate ordered pairs that approximate a solution. The smaller the step size, the closer the approximation. I kind of put this method down here. It's in algebra form. You start with a point, and to get to the next x1, you're going to add the step size. That's easy. I mean, adding the step size to the x part's easy. It's the y part that you just have to think about. What you really want to know is this is the slope of the previous point. So you multiply the slope of the previous point by the h value is the delta x, and then you add it to the y value from before. So this whole slope of previous point times delta x, this gives you actually the delta y. That gives you a little bit of a change, what the little bit of change of y is going to be. And then you add it to the previous y, and you can see where the new point is. And then you just continue that pattern. This is the same thing as before, but you know, 2's replace 1's, and 1's replace 0's. So let's do another example. Given the differential equation, dy dx is equal to x minus y, and our initial point of y0 is equal to 4, let's find y of 1 with 2 steps. 2 steps means 1 step, 2 steps. Means that my delta x, also called h, is just going to be equal to 0.5. Not a very good approximation, but it will get us there quicker. So we just need to take 2 steps or 2 walks. These take a while, so we don't want to do too much, but you'll see some examples that have these in tables. You just don't want to make sure you get them right every time. Okay, so my initial point, I have 0, 4, and here's one of the ways that we see this. We have, I'm going to have x and y in a table like this, and then I'm going to have my delta x. So if my delta x is 0, this is my starting point, 0, 4, and then if my delta x is 0.5, which is the next step, then my x is actually going to be 0.5, and the y, I'm going to take that 0.5, multiply it by the slope. Now the slope at 0, 4 takes these and plugs them in here. So you get 0 minus 4, which is negative 4. And then you're going to add the y value from before. So 0.5 times negative 4 is negative 2. Negative 2 plus 4 is 2. Okay. Now we're going to repeat the same thing. My next delta x is still 0.5. But I'm now at 1.0 greater for the x, so my new x is also 1.0, or 1. Now what I'm going to do is I'm going to take that same delta x, maybe I should keep this as 0.5 so you don't get confused by that. Delta x is always going to be 0.5. This is just depending on where I'm starting. I'm going to take that same delta x, I'm going to multiply it by the y value from before. Sorry, you can tell this is the first time I recorded this, but I knew that was wrong. I'm going to multiply it not by the y value from before. I'm going to multiply it by what dy dx is when I plug that in. So let's kind of do a little sidebar here. Dy dx equals, I want to use the previous point, so this 0.5 and this 2. So dy dx is equal to 0.5 minus 2. It should not be. Sorry, I thought I had a denominator there. 0.5 minus 2, which is negative 1.5. So I'll go ahead and write that in there, negative 1.5, and then plus the previous y value. So 0.5 times negative 1.5 is negative 7.5, which is negative 5.5. So I'm going to erase this. Let's go negative 5.5, and then we're done. So y of 1 is approximately negative 5.5. Let's try this again. Hopefully I'll be a little more smooth on this one. I'll set this up like I did before. We'll have an h or a delta x, whichever one you want to call it. I've seen them both and haven't picked out one or the other. That's why I switched them here. X and y. Let's make this a little bit wider so I have more room. H is going to be 0.25 across the board. I'm going to start at the point 0, 1. And here's my differential equation. It's only dependent on x. If you look at that, that's a little bit different. So I want an approximation of y1, of y of 1, and I'm going to increase by 0.25. So I've got to go more steps here. Okay, so we increase that by 0.25, which means that we're going to take the that 0.25, which is the h, and multiply it by, plug 0 and 1 in, and I get negative 1/4, because y really doesn't go in there at all. If I get negative 1/4, then I'm going to add the previous y value. So this is 1/4 times negative 1/4 plus 1. This is 15/16. Yeah, I'm switching to fractions because this is probably going to be a little bit easier to make fractions. So the next one is 0.5, or 1/2. And my step size, though, is still 0.25. It's still 0.25. So I'm going to do 0.25 times. Now, if I plug in the previous ordered pairs into the differential equation, I'm going to get 1 over 1/4 minus 4, which is 1 over negative 3/4, or negative 4/3. So I get negative 4/3, and then plus the previous y value of 15/16. So that's actually the same thing as negative 1/3 plus 15/16, which is, I'm going to pause this, 29/48. Two more steps left. We got 0.75. I'm going to do 0.25 times. Okay, we need to plug the new slope in. So this is 1 over 1/2 minus 4. 1/2 minus 4 is 3.5, or 7/2, so that's negative 7/2. But that's 1 over, so that's inverted, so negative 2/7 plus 29/48. And you bet now I'm using a calculator on this one. And that gives us 179/336. And then lastly, we're going to do another step to get to x equals 1. And I have 0.25 times 1 over 1 minus 4 is negative 3, plus 179/336. Oops. And I end up with 151/336. And that's my final approximation of y of 1, because I've reached it. And it's still an approximation, but that's a very good one because I used a small step size. And we're done.